Hi class, we are on the next section of chapter 11, 11.4. Today we're going to talk about shifted conics. So really what we're doing today is like we did in chapter 2, where we took a function and we talked about how to shift the function up and down, left and right. When we're talking about functions, however, we talked about stretching them, compressions, things like that. For these conics, we're not going to talk about stretching or compressing them. We actually already talked about that when we talked about creating the conics, right? Because if we stretch or compress a conic, then really we're affecting the major and minor axes, or the transverse axis, or the width of the parabola. So what we're focusing on here is really just moving these conic sections up and down, left and right, and how to find the equations based on those shifts, or how to find the equation based on the shift. Okay. So one of the things that we really want to focus on when we are talking about shifting a conic is focusing on what the center is, and understanding that the new center changes where my axis of symmetry is, where that major axis is, where that minor axis is, or that transverse axis. Once we understand that we've now shifted our conic and the center is somewhere different, everything has to be related to that center, which is one of the reasons why when we derive some of the equations and the formulas that we had in the previous sections for these conic sections, I did it in general. Like for the parabolas, I talked about everything with reference to the line of the directrix, rather than saying, hey, let's center this on the center of the graph at the origin and talk about everything from there. I said, let's talk about this from the directrix, because the directrix can be really anywhere in space, and then it's a lot easier to talk about what our conic is. Okay, so let's do an example. It's an easiest way to kind of start this off, because we understand how shifts work, right? So here we can see that we have a completely different center. If I did not have this -3 and this +2, this would just be a regular ellipse. I know it's an ellipse because both signs are positive and it's equal to 0. I would have a major axis of length 12, right? Because remember, it's whatever the square root of this doubled. The minor axis would be of length 8, okay? And because I know that from the center to the edge is 6, and the center to the edge here is 4, so there's 2 of those, okay? I also know that the major axis would be along the y-axis, and the minor axis would be along the x-axis. Now I take all that information and I just shift it, right? I shift it down 2 units and right 3 units, and that is where my center is. So I still have a major axis that has a length of 12, or from the center of the ellipse to one of the vertices for the major axis has a length of 6. And so I move down 2 and over 3. So from 3 to one edge on the right side, that means I would have a vertex at 9. If I go in the other direction, that means that the other vertex would be at -3, right? So I'm really just kind of understanding that my center is somewhere different, okay? And I want to know how it's different. Figure out what that center is, and understand that now my major axis, okay, since that's along y, is no longer on y, but it's on the line y equals -2, okay? I'm sorry, x equals -2. And my minor axis is it goes along the x-axis, right, for the minor, and that's centered at x equals 3. Okay, so my minor axis is at y equals -2. Okay, running parallel to the x-axis. So again, it used to be centered at at x equals 0. Now it's centered at x equals 3 for the minor, but the minor axis runs lengthwise with the x-axis, right? But it's been shifted down 2 units. Okay, and it has a length of 8, right? So again, from the center to one edge is 4, from the center to the other edge is another 4, so it has a length of 8. The major axis is centered at the line x equals 3, okay? So remember, x equals 3 is a vertical line. Okay, and my major axis is along y, so it's vertical. So it's vertical at this x value instead of x equals 0, because I've been shifted to the right 3 units. So instead of x equals 0, or the y-axis, it's at x equals 3. Okay. And again, it runs parallel to the y-axis because it's been shifted over 3 units. And it has a length of 12 because from the center to one edge is a length of 6, right? So from the center to the other side is a length of 6, so total that's 12. This means that the minor axis of vertices are, so I take this point and along, so for the minor, so that means I change left and right from this point by 4 units one way and 4 units the other way. So that means that if I'm centered at y equals -2, that this value isn't going to change, okay? But the x values are going to change. So I'll be at -2 for y, but then I'll move 4 units for this. So that means it'll be 7, -2, and -1, -2, okay? So 3 plus or minus 4, -2. That's how I figure this out, right? So to the x value, I will add 4 and I will subtract 4, and that will give me my 2 values for the minor axes. One way to really help with this is to just draw a graph, right? As you start to like label your things, draw a little graph to help you out. I mean, I've done this a lot of times, so I can do it in my head. Obviously, we're going to draw a graph at the end, but I can't draw a graph as we're going through these, but we're working. This is the best I can do to like describe to you how we're doing this. But when you're doing this for yourself, you definitely should have your piece of paper and kind of saying, oh, here's my axes, here's my center, this is where the minor is, this is where the major is, and kind of keep track of those things and draw your graph as you do this, right? So my major axis vertices are the same thing. I'm going to take 3, -2, and I'm going to plus or minus 6 to the y values, okay? So I'm going to take -2 and add 6, I'm going to take -2 and minus 6, and that gives me my major vertices at 3, 4, and 3, -8. Okay, now to find the foci works the same way. It's still c squared equals a squared minus b squared. And once I find the value of c, remember c is the distance away from the center. So I do the same thing that I did for the minor axes and the major axes. But first I have to find the value of c. So I know that this is my a, this is my b, sorry, a squared and b squared. So I'm going to take 6 and 4 and do the Pythagorean theorem. So c is square root of 36 minus 16, which is 2 root 5, right? The difference here is 20, so simplify 20, I get 2 root 5 for c. So I'm going to take, it would normally be at 0 plus or minus 2 root 5. So I'm not centered at 0 anymore. I'm centered at 3, -2. So I will plus and minus 2 root 5 from this value. And since my major axis runs vertically, that's going to be applied to the y values of the center. Okay, so this is what it would look like. So 3, -2 is in the new center. I didn't put the foci here, but this is the major axis. Okay, this is the long ways, right? This is the short ways. So this is the minor axis. So from here, I move a distance of 4, distance of 4. From here, a distance of 6, and a distance of 6. Okay, and then plot my thing, right? My vertices are at 3, 4, 3, -8. Okay. 3, 4, 3, -8. Okay. And -2 and 7, and -2, -1. I'm sorry, -1, -2. Okay, so -1, -2, and 7, -2. So this matches up with everything that we had before, right? So that was an ellipse. If I had to do it for a hyperbola, I would do the same thing. For a parabola, same thing. Everything is the same. Figure out the center and just apply everything based on that shift, right? The shift of the new center tells us where everything is. All the axes, transverse axis, where the foci are, where the axis of symmetry is. All of that stuff is related to the center. Okay, so once I have done that, I change everything else accordingly, right, as we saw in the last example. Now, there's a general equation for any conic, okay, for any conic. So a shifted conic, a rotated conic, any of those things. A regular conic section has a general equation, and that's what we're going to talk about right now. This is the general equation for any conic section, okay? So again, whether it's been rotated, shifted left, shifted right, shifted up, shifted down, anything. This is the general form. Just like we have a general form for a polynomial, or for a polynomial, for a quadratic. We don't know anything about the quadratic until we actually put numbers to it, right? Same thing here. All conics have this form. Some things might be multiplied times 0, so they disappear, right? But they all have this form. So you have an x squared term, a y squared term, just an x term, just a y term, a constant term, and a one mixed term. Okay, so all conics have this equation. And based on what's actually there, what the coefficients are for A, B, C, D, E, and F, will really tell us what kind of conic we have and the properties it has, right? We can take this general form of a conic and we can transform it into the general form of an ellipse, the general form of a hyperbola, or the general form of a parabola generally by completing the square. Okay, so we know that the general equation for an ellipse, for example, looks like this. Okay, so if I took that general equation for a conic that I just had and completed the square for x and for y, this would be some combination of the A, B, C, D, E's, and F's, right? This would be also some combination of A, B, C, D, E, and F. So those constants would turn into these values. Okay, but I can manipulate that equation to look like this for an ellipse, or the standard for a hyperbola or parabola. Okay, so if we try to put this into the form of whatever conic that we think it is by simplifying by completing the square, and it turns into a system of equations, just two lines basically, like a line. Basically, let's say the x squared and y squared term drops out and the bx y term drops out, and I turn into just something like dx plus y plus a constant. It turns into just a line, okay, or even just a single point, right? Then it's called degenerative, because my general equation for a conic doesn't actually provide a conic for me. It degenerates into a first dimensional, first degree equation, right? A line or a point, or a 0 degree in that case. So if A or C is non-zero, okay, so if this is present or this is present, then we're going to have a parabola. Okay, if A and C are the same sign, then we're going to have an ellipse. Okay, if A equals C, then the equation is a circle. So if this is 2 and this is 2, we'll have a circle, for instance. So here, for one, just to talk about this for a second, it says if A or C is non-zero, then the equation represents a parabola. So that doesn't mean both of them non-zero. Okay, this is an exclusive. One of them is 0, the other is not. So if this is 0, I then have a parabola because there's only one square term, right? It would be y equals some number with an x squared, so I would have my my parabola with the axis on the y-axis, right? If this is 0, but this is non-zero, then it's rotated 90 degrees and the axis of symmetry is on the x-axis, right? So for one, I just want to be very clear here. It says A or C. That does not mean that they're both non-zero. It means that one of them is 0 and the other one is not, okay? For 2, to have an ellipse, I have to have both x and y present, x squared and y squared present, I'm sorry. So if both of these are non-zero, if both of them are non-zero and have the same sign, then it's an ellipse. If the coefficients are the same, it's a circle. If one's positive and one's negative, then it's going to be a hyperbola, because remember, a hyperbola has the same form, but there's a subtraction between them. So depending on A and C, what's going on for A and C, it's easy to tell what I have. So again, if I only have an x squared or only a y squared, parabola. If they're both positive, it'll be an ellipse. If they have different signs, if one's positive and one's negative, it's a hyperbola. And if the values for A and C are identical or the same, then it's going to be a circle.